Okay, now I am recording perhaps. Yeah. So now you can put in your attendances and then. Yeah. So anyway, L equals half mr dot square minus q phi plus uh, q a dot r dot. So this I tried to convince you uh, that okay, this is one of the Lagrangian that gives me the correct equations of motion. Now, using the four vector notations, so I used AMU equals phi a, and so J mu current density equals rho, and here rho times V. You could show that this interaction term can be expressed as J mu A mu, the extra term. So today we asked the question, okay, so far so good. So if we had to guess the Lagrangian, suppose we did not know the Lorentz force law. Okay, so I got it from Lorentz force law, right? Suppose we did not know the Lorentz force law, then could we arrive at this Lagrangian? Okay. But then you have to understand that we cannot arrive at this Lagrangian without any input. So what kind of inputs we'll have? We will have here. Okay. So here the input we will have is something called the gauge symmetry. So you have perhaps seen that this phi and a are not unique. Okay. So if you change this a to say a prime, which is equals a plus grad f. Okay. So this f is a function of rt, and you change phi to phi prime, which is equals phi minus del f del t. Then the physics remains invariant under these changes. So no physical implications. So if there is a transformation which leaves your physics invariant, then you call the transformation as symmetry. So this transformation similarly we'll call it the gauge symmetry. Okay. Now your Lagrangian, so suppose if you change this to this and you substitute it in the Lagrangian here and here. Okay. So if your L changes to L prime, then if this is a symmetry, then you must understand that this L and L prime are equivalent. Okay. All right. So let us see what this L prime is. Okay. So this L prime is so I will only write the interaction part. So I will write q phi prime plus q a prime dot r dot. Okay. So which is given by minus q times phi is phi minus del f del t, and plus q a prime is a plus grad f dot r dot. Okay. So now you see if I collect it. So first I collect this term and this term. So I write minus q phi plus q a dot r dot, and the extra term I have can be written as del f del t plus grad f dot r dot. Now again you can notice that so if I write, so this is my old Lagrangian, so this is your L, plus this extra term from yesterday's exercise is the total derivative of this f. Okay. Now remember, f is a function of coordinate and time only. Okay. So this L prime and L are equivalent. That means this gauge symmetry is still a symmetry of the Lagrangian. So now you start to wonder that if we demanded gauge symmetry from the beginning, suppose somehow we know that the nature must obey gauge symmetry. I'm not explaining how do we know that nature obeys gauge symmetry. Suppose we knew that nature obeys gauge symmetry, then what would happen is that you can reverse engineer. So start from this. So you must require that whatever Lagrangian you want to write, that Lagrangian must be equivalent. So if it changes to L prime, must be equivalent, and then you start from here. So L prime equals L plus df dt, and you want a Lagrangian in terms of phi and a, such that if you make these changes, the Lagrangian transforms into this. If you want that, then this is the simplest Lagrangian that you can write, and this is kind of a reverse justification why this works. We will try to get a better understanding of why it is so sacred. These gauge symmetries are why this is so sacred. But if you, but for now, the lesson is the Lagrangian that we obtained for electrodynamics here, the interaction Lagrangian, and that truly reflects the nature of electrodynamics. That means that that Lagrangian does not sense this gauge transformation. Like if you change the fields, so this A and phi I will call for some reason fields. I have not introduced this. So if I change this A and phi by this transformation, the Lagrangian, the change in Lagrangian is just by total derivative, which does not affect my equation of motion and does not affect the physics at all. So this is kind of satisfying to know that the Lagrangian we have landed at for electrodynamics is perhaps the correct one. Okay, so now I will move on to a different topic. Now I need to know if you have questions up until this part. So there's Lagrangian formulation of a particle in an electromagnetic field. If you have questions about that, you can ask me now. Okay, so I assume that yes.
The potential has a uniqueness property.
That's from uniqueness theorem. That is a different thing. So uniqueness theorem tells you that if you are solving the potential from a Laplace equation or a Poisson equation, and the boundary conditions are given, then the potential inside the volume is unique. So it's not related to this thing.
Okay, sir.
Okay. Uh, all right, and that also holds for electrodynamics. Sorry, electrostatics only. Uh, Anything else? All right. Okay. Now I will move to a topic called the small oscillation. It's a bit of a diversion. So there are two terms here. So one is small. What do I mean by that? And another term is called oscillations. Okay. So I will explain first what do I mean by that. So I will borrow your intuitions from the usual case of the simple harmonic oscillator. So for the simple harmonic oscillator, you know the Lagrangian is let me use this. So p square over twice m. I am talking about in one dimension minus half m omega square x square. This is the Lagrangian, and this fellow, this is a Bx. Okay. Now the thing is, if you now try to plot the potential, okay, then the potential is minimum at x equals 0. At x equals 0, the potential reaches a minimum, and about this minimum, you suppose disturb this. So this is my Vx and this is my x. Okay. If you disturb the system by a small amount, there is a restoring force that comes into play, and it try to move it to the equilibrium position, and due to inertia then it overshoots and then it oscillates like this. Okay, so this is how it happens, and the oscillation is simple harmonic if your potential is quadratic in your coordinates. Okay. But in general, the potential need not to have this nice form. Okay. So what I will assume in general, that I have a potential which is a function of the generalized coordinate, okay, and up to say qn. Okay. And this potential suppose has some local minimals. Okay. So about suppose one of the minima occurs at say at q equals qk equals q0k. Okay, so one of the minima, so minimum is at qk equals q0k. The value of qk at which and I run it for all the case. So k equals 1 to blah, 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 to n. Okay. So at this point, the minimum of the potential occurs. Now, so even if my potential behaves a bit weird, so now my potential may look like this. It's not, you see, it's not this simple harmonic motion. But if I concentrate my views at a small distance from the minimum position, so from here to here, let's say, I can still approximate it as a parabola. Okay. And it will, so as long as my displacement from the equilibrium, my displacement from the minimum of the potential is small, and that's the meaning of small here, I can approximate the potential to be a quadratic one, and I match it with my simple harmonic potential, and it will undergo an oscillation, and I can express it. I can express the oscillation formula in a nice manner, and that's why the name is small oscillation. Okay. So this is the idea. So I will expand the potential about a minima. So if the minima is occurring at qk equals q0k, and the displacement from the that I will denote by xk. Okay. So xk is kind of this amount, this yellow amount. So if I am so now if I relabel my coordinates, if this is my qk direction, so then this is q0k, and so at q0k basically you have the minimum, and this so this distance here is xk. Okay, let's say I'm doing that. Okay. So what I can do is that I can Taylor expand this potential about that minimum. Okay. So I can write my V equals V0. So V0 is basically V at Q0K. I mean all the coordinates combined, okay, plus summation over k del v del qk evaluated at, of course, qk equals q0k times xk, the displacement, plus summation over uh, 1 by factorial 2 probably jk and del 2v del qj del qk. These are evaluated at qk equals q0k and xj xk. Okay, plus other terms, but as long as my xj and xk are small, I will terminate the series here and I will ignore terms of order x cube because those are small, let's say. Good. So since the point qk equals q0k is a minima, I can readily see that this term doesn't contribute, so this is 0. Okay. And this is of course a constant. So and a constant added to the potential doesn't matter. Okay. So what I can write is that my potential V can be approximated as, so my V can be approximated as half summation over jk eta jk xj xk. Okay, so where my eta jk is del 2v del qj del qk at qk equals, or I just put the index 0 here, that means it is evaluated at the minimum. And so you note that this eta jk is symmetric, so it's a symmetric n cross n matrix. Okay, so that this follows from my definition. So as long as my oscillation is small, so my amplitude for oscillation is small, I can approximate the potential as a quadratic function of the displacement from the equilibrium position. So that's the main thing. So as long as my my amplitude of oscillation is small, the displacement from the equilibrium position is small, I can do that. Okay. And as I have shown previously, the kinetic energy can usually be written as a quadratic function of uh, of the generalized velocity. So I can write it as mjk xj dot xk dot. Okay, so this follows from our previous things. Okay, so it was, if you remember, it was qj dot qk dot qj dot qk dot it was, but as long as qk is equals this, and this is a fixed position, this is a constant position where my minimas are occurring, then you have qk dot equals basically xk dot. There is no ambiguity there. So the generalized velocity is rewritten as xj dot xk dot, where xj is the displacement from the equilibrium position in the jth direction. That's it. Okay. So this is my T and this is my V. Since I am implicitly assuming that the force can be obtained from a potential of this form, and this potential is a function of coordinates only, uh, it's fine to write my Lagrangian as T minus V. So this, my Lagrangian would be T minus V. And so my Lagrangian would be given by half then jk m jk xj dot xk dot minus eta jk xj xk. Okay, so this is my Lagrangian. Okay, I will use a more unified notation. So the notations I would be using is the matrix notation. So this I can write it as half x transpose times eta times x. Okay, so this x is a column matrix. So I will, and this one I can write it as half x dot transpose, then m, then x dot. Okay, so in this notation, basically in this notation, x is a column matrix, x1 dot 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 up to xn. Okay, and that's why this multiplication makes sense, and if you do the multiplication you will precisely get this and this. Okay, so later it will be useful when I will be talking about matrices. All right then. So I have found my Lagrangian. So now for the jth equation of motion, okay, so the uh, so equation of motion for xj rather can be written as d dt of del L del xj dot minus del L del xj equals 0, right? So if you do the differentiation properly, what you will get is that so summation over k m j k xk double dot plus summation over k eta jk xk equals 0. So notice that there is no summation over j here because you are different, and j can take values from 1 to n. So there are n equations like this. So for j equals 1, you have one equation. For j equals 2, you have another equation. For j equals 3, you have another equation, and so on and so forth. Okay. Now, so this equation I can again compactly write as m times x double dot plus eta times x equals 0. Okay. So where again this eta is a n cross n square matrix, the m is a n cross n square matrix, and x is an n component column matrix. For people who are new to this, you can try to visualize this multiplication as this is a square matrix n cross n, this is my m, and then you have a column matrix, this is your x dot, plus another square matrix, this is eta, and plus another column matrix equals to 0. So if you do the multiplication, so this multiplication will give me one column matrix, plus this multiplication will give me another column matrix, and that is equals to 0. And since these are n entry column matrix, so that gives me n equations. Okay, clear? And those are the n equations that I am trying to solve. Okay. But so before I proceed, there is one striking resemblance to our known equation of motion. So this is the thing. So if you look at this equation, this mx double dot plus eta x, it looks strikingly similar, say, for one-dimensional simple harmonic motion, right? Where we have mx double dot plus kx equals 0. Okay, and you divide by m to write x double dot plus k by m, which you write is omega square x equals 0, right? And this k is kind of the restoring force, and m is the mass of the thing. And here also m is the analog of mass because it comes from my kinetic energy, the quadratic coefficient of my kinetic energy. And this eta is usually called the restoring tensor. A tensor because it has two indices, okay, like moment of inertia. Restoring tensor. Okay. So now I see the similarity between my simple harmonic oscillation and this equation, this n number of equation. Only difference is that unlike the simple harmonic one, this x is a column matrix and this m and k are matrices. Okay, so I cannot straightforwardly write my k by m as straightforward as omega square, but I somehow can feel that my solution can be oscillatory. My solutions will be oscillatory. Okay, because because of the very nature of the equation, and I know that um, one a similar equation gives me oscillatory solution, basically simple harmonic motion. So with this spirit, what I do is that we assume the solution to be of uh, uh, e to the power I omega t. Okay, so what I write the solution will be, say, x equals a times e to the power I omega t. Remember, this x is a column matrix. Okay, so this x is a column matrix. So what I mean by this is, so this actually breaks down to x1, x2, xn equals this a1, a2, dot dot an I omega t. This is my solution. That means the my kth coordinate, uh, so xk will be oscillating with ak e to the power I omega t. Now, unlike in the usual simple harmonic scenario, I cannot determine the omega in a straightforward manner here, okay? Because here my omega was basically square root of k over m, because k and m were numbers. But here, in a similar way, I cannot just write omega is my eta over m, because these are matrices. So what do I mean by division of matrices? Okay. But then I need to find out the frequencies that with which my xk is oscillate. Okay, so for that, let us substitute this into this one and see what happens. So if I substitute the matrices there, then what I should get is that minus m times a times omega square, because you are differentiating twice, and times e to the power I omega t. So what I can write is like this, plus eta times a times e to the power I omega t equals 0. So I can forget about this part and I can write this equals 0. So this is the equation that I need to solve. Now, again, I want to write the equation in a cleaner form. So eta minus omega squared m. Omega square is a number. Remember, omega is a number. Omega square m, okay, times a, that is equal 0. Okay. So first of all, you should notice that this is a n cross n matrix. Okay. So this matrix is of the form this n cross n matrix, and this is a column matrix. So this is of the form like this, and this is equal 0. And you remember, you have to solve for omega as well as the amplitude. So these are the unknown quantities that I introduced in my trial solution. Okay. So so this kind of gives you n number of simultaneous equation for A. So n simultaneous equations, not just equations, it's just linear equations for a1 to an. Okay, so if you so now a trivial solution will be all the a equals 0. Okay? All the an equals 0. So the trivial solution is that a equals 0. That means all the component of a to be 0, and then you trivially satisfy this equation. But for non-trivial solution of this equation, you must have the coefficient determinant to be 0. So that what you mean is that not all the equations are independent. So for non-trivial solutions, so by non-trivial solution I mean that some of the ans are not 0. So the non-trivial solution, which I mean by that is that not all ak are 0 simultaneously. So for that to happen, what I need to have is I have to check the determinant of this coefficient matrix, and I equate this to 0. Now at this point, tell me if everyone understands this step. I mean, this is perhaps a common step. You have been using this in many times, but if someone is shaky about this thing, that person should just raise your voice now. Then I can explain a bit further, otherwise I will move on.
Yes, sir.
Okay. So everyone is okay with this step. All right. So for non-trivial solution, you have the coefficient determinant to be 0. Now, so this is a determinant, and this contains omega square. Okay. So you can just call it this omega square. You can treat it as, let's say, I'm renaming it as let's say y. Okay, y is just a number, and the determinant. So if you take this determinant, since this is an n cross n matrix, that would be a nth order polynomial in y. Okay. So if you expand this determinant, then that would be an nth order polynomial in y. Okay, or in omega square. Whenever I say y, I mean just omega square. Omega square is a number, remember. And that means the nth order polynomial equation that is equals 0. So then this omega will have n number of roots. Okay, so this omega square will have n roots. Okay, the alphath root. So for when I am talking about the root of omega square, and I will talk about the alphath root, I would be denoting by omega alpha square. So the roots would be denoted by the Greek symbol, and the coordinate components would be denoted by Roman symbol like JK, etc. Okay, so it will have n roots. Again, if you have trouble, you every time you just compare with your one-dimensional case. So in the one-dimensional case, what did I write that? My one-dimensional case here. Since these are 1 cross 1 matrices, so that's why your omega square had only one value, which is k over m, nothing else. So you just have one root. But you will see if those are just 2 cross 2 matrices in general, n cross n matrices, then omega will have many different roots. So these are basically compound oscillations that you have to take care of. So the alphath root I will denote by omega alpha square. Okay, and these roots are called the normal frequencies. So these are called normal frequencies. Okay, and sometimes you can also see the word normal modes of oscillation. Okay, So the roots of omega that you find out by solving this equation is your normal frequencies, are your normal frequencies. All right. So now if you find omega alpha square in principle, suppose for alpha equals 1, 2, or 3, for a particular alpha, you substitute it in this equation. So you substitute omega alpha in this equation. Suppose you put omega alpha square same equals 0. Now this matrix is totally determined because at the beginning you did not know. It's like the eigenvector problem in your linear algebra. Okay, so now you have basically substituted the eigenvalue. Now you have to find the eigenvector. Okay, so you find the eigenvector and you write the solution as for alpha its solution. You can write the solution to be ak alpha e to the power I omega alpha t. Okay, so this is my alpha th solution. All right, so this is my alpha th solution. So in general, the general solution for xk, okay, would be, so this is my, let's say xk alpha is the alpha th solution for xk. Okay, so my general solution will be, so xkt that I intended to find would be summation over alpha equals 1 to n, okay, a k alpha e to the power omega alpha t, the linear combination of all the oscillation modes. Okay, so in the matrix notation, what you have is that you write xt, where x is a matrix, then again alpha equals 1 to n a alpha e to the power I omega alpha t. All right, so this is now, so this thing is now a column vector, and this is basically the sum of column vectors. Like this whole thing is sum of column vectors, so the linear combination of all the modes. Okay, so this is a general strategy that you have to follow to solve a problem of small oscillation. I will come to some examples for that. And before that, I would want to discuss a few more little things. But let me know if you have questions up until this point. The procedural thing, do you understand the procedure? That given any problem of small oscillation, you can use this method to arrive at a solution. Okay. No questions then? All right. Good. So now to proceed further, I need to convince myself that this solution of omega square that I am finding, each of the solutions are real. So remember, this e to the power I omega t will actually represent an oscillation if omega is real. That means if omega square is real, or omega square is of course real as well as positive. Okay? Because if omega square is negative, then omega will be purely imaginary, and then it will no longer represent a solution. It would be either exponential decay or something, exponential growth or something else. Okay, it will not be an oscillation. So to convince myself that we are actually getting an oscillatory solution, we need to first get convinced that this omega alpha square is positive for all alpha. Okay, this is the first thing that we need to understand. That how can we understand that? So first, let me go back to the main equation, that is the eigenvalue like equation that has like eta a equals omega square times MA. So M and A are matrix, omega is a number. So that is this equation. Okay. So this is the equation I am rewriting here. Okay. And for the alphath root, you can write down that thing, that the alphath root. You can write down that eta times A alpha equals omega alpha square times M times A alpha. This is for my alphath root. Okay. The alphath root. Okay. And for the, say, beta-th root, you can write eta times A beta equals omega beta square times A beta. So this is my beta-th root. Okay. So if you take the Hermitian conjugate of this equation, so I take the Hermitian conjugate of this equation, and remember both eta and M are real and symmetric. So eta and M are real symmetric matrices. Real symmetric is another way of saying Hermitian matrices. So what you have is eta dagger equals eta and M dagger equals M. Okay. That follows from the definition of those quantities. All right. So what you have is you will have A beta dagger times eta equals omega beta square star. So I do not know yet my omega b square is real or imaginary or so on and so forth, times A beta dagger M. All right. Now I multiply this equation. Let me use color. So this equation over here with A beta dagger from the left, and this equation here with A alpha here from the right. Okay. So you can easily see what will happen. So on the left hand side, both of these equation will have A beta dagger eta A alpha, and this will have A beta dagger eta A alpha. And now if we subtract one from the other, what I will have in the left hand side, I will have 0, and that is equals to omega alpha square minus omega beta square star times A beta dagger M A alpha. All right. Now if I impose again beta, this is for any general beta and alpha, but now if I impose beta equals alpha, the case with beta equals alpha, I will have 0 equals omega alpha square minus omega alpha square star times A alpha dagger M A alpha. Okay. Good. Now, first of all, this A alpha dagger M A alpha, I have to prove that this is real. Okay. So now there are two pieces. First of all, if we could equate this to 0, then I would readily conclude that my omega alpha square is real. Okay. But to do that, I have to first show that this is non-zero. Okay. So I have to first show that this is non-zero. Then can I only say that the thing that is multiplying my A alpha dagger M A alpha is 0. So first of all, I call this thing, let's say, Z alpha alpha. Okay. First, I notice that this is real. Okay, so I can write down, say, Z alpha alpha star, which is basically A alpha dagger M A alpha the whole thing has staggered. Okay. So if you evaluate this thing, you will find the same thing, which is Z alpha alpha. Remember, M is real and symmetric. So this Z alpha alpha is at least real. Okay.
Sir, Z alpha alpha dagger star.
Z alpha alpha is a number, so it doesn't matter if you are considering
Okay.
dagger or star. Okay.
Okay.
So it's the row matrix. Is Z alpha alpha is a number. So this thing is a number. Okay. Good. Now, to further convince yourself that this Z alpha alpha is real, let us split Z alpha alpha. Let us so Z alpha alpha is real, but I do not know if this A alpha is real or not. So if I do not know anything about A alpha, so I can write down A alpha as X alpha plus I times Y alpha. So these are real column matrices. So this X alpha and Y alpha are real column matrices. So this is a real column matrix, and this is also a real column matrix. So these are real column matrices. Okay. So if you now actually calculate Z alpha alpha, which is A alpha dagger M A alpha, what you will obtain is X alpha transpose, because X alpha is real, so that's why I am using transpose here. So dagger is equivalent to a transpose plus Y alpha transpose Y alpha, and then I times X alpha transpose M Y alpha minus Y alpha transpose M X alpha. You can check that. You just expand it, put it in there, and this is the thing. Now, in the imaginary part, you can easily check that this and these are the same thing. So this is also a real number, and this is also a real number, the transpose of this real number. Since this is a number, the transpose and the number are the same thing, so these two cancels out. So these two are numbers. So what you are left with as expected a real quantity, and which takes this form. Okay. So X alpha transpose M X alpha and Y alpha transpose M Y alpha. Okay. So this is my thing. Okay. Now I have to prove that this is positive. I will use it later, but for now I want to prove that this is positive. To see that this is positive, I can go back to the expression of kinetic energy. So my kinetic energy was given by half x dot transpose dot m x dot. Okay. Or if I rewrite it in another way, x dot equals 2 times t. Okay. Now, of course, the kinetic energy is a positive definite. It's always positive. So I see that if there is a velocity matrix transposed here, and the what I call this M is my mass matrix, let's say. So if the mass matrix sandwiched between two velocity matrices is always a positive definite. Okay. So I did not say what are my velocities. The velocities can be anything. So for any arbitrary velocities, this thing is a positive definite. So this thing is a positive definite. Okay. Now look at this structure. Doesn't it look the same with this one? So this is the same as this 2 times t. Only difference is that my velocity matrix is replaced by X alpha transpose. So in the case my velocities happen to be equal to the entries of this X alpha, like numerically equal to the entries of this X alpha. This is my kinetic energy. Okay. So what I have here, so this is some form of say 2 times t prime. So t prime, because this is the value of kinetic energy when my velocity matrix happens to coincide with x alpha. And this is some 2 times t double prime. Okay, so this is my 2 times kinetic energy when my velocity matrix happen to coincide with y alpha. Okay, so that means this alpha alpha is definitely greater than 0. Okay, so these two is the sum of two positive definite things. Okay, and remember a alpha is non-trivial, so not all these things are 0, so it's not 0 and it's a positive definite then. Okay, so since it is a positive definite and it's non-zero, and that means this quantity needs to vanish to have this to be 0. And now at the first stage I conclude omega alpha square equals omega alpha square star, that is omega alpha square is real. So the first stage I understand that this omega alpha square is real, as it is supposed to be if it has to represent a frequency. Okay, now if you see that how do we obtain this omega alpha square. Okay, for example, from this equation, let's say. Okay, so this equation I will rewrite. So this equation, notice again very carefully. So eta times a alpha equals omega square m a alpha. All right, right, omega alpha square. Now, if I multiply by a alpha dagger, then a alpha dagger a alpha equals omega alpha square a alpha dagger m a alpha. Okay, so now I can omega alpha square I can write down as it, because this is a number, this is a number again. So these two are numbers. So I can now what I am doing is division of numbers. So a alpha dagger eta a alpha, then a alpha dagger m a alpha. Okay. Now notice that this a alpha dagger m a alpha, I have already said that it is a positive definite. It is precisely the same thing. This is my z alpha alpha. And what I use to prove that is m is a symmetric matrix and the kinetic energy is a positive definite. Okay. These two things are I had used. Okay. Now eta is also a symmetric matrix, and the potential, if you take at the equilibrium point the potential to be 0, then any deviation from that will give you a positive potential. So I am not going into the details, but by the same token I proved this quantity to be positive definite. This can be also be shown to be a positive definite. Okay, you can just call it say y alpha alpha and proceed in the same way as I did here, and convince yourself that this y alpha alpha is a positive definite also. So then omega alpha square is the ratio of two positive definite quantities. Now I can confidently say that omega alpha square is a positive definite. So that means the frequency eigenvalues that I am getting from this exercise are real and positive, and so that actually gives me oscillations. Okay, it's not other thing. It's not exponential growth or exponential decay. These are real oscillations. Okay, so I will close my lecture for today here, and I will ask if you have questions. Tell me. Okay, so I just assume that there are no questions. Hopefully it was clear, and Was it too difficult for anybody? I don't know. I did not get any impression. So all right then. Let me stop recording.